Welcome to Center Math's Advanced Knowledge Problem of the Week. For this week's problem, we want to prove that an integer divisible by two unique odd primes cannot have a primitive root. So it doesn't have anything that the minimum power, so if we have an integer n, there's no g, so g to the totient function of n is congruent to 1, and no lower power. That we're trying to prove does not exist. So first we're going to have some preliminary results. So the first thing we have is if we have a to the I congruent to 1 mod m, a to the j congruent to 1 mod n, and the greatest common divisor of m and n is just 1. We can say a to the I times j divided by the greatest common divisor of I and j is congruent to 1 mod mn. And this is because we can look at this two ways. We can look at this as I times some factor k, which is j over the GCD of I and j, or j times I divided by the greatest common divisor. And in either of these cases, so the power is just, that would just be a to the j to some power, which has to be congruent to 1 mod n, or a to the I to some power, which also has to be congruent to 1 mod m n mod m. And so because these are relatively prime, this is divisible by m and also divisible by n, so it must be divisible by m times n. So this holds. Another thing we can say about the totient function of the greatest common divisor, the totient functions of two numbers. Note, so we can write the totient function of m as n times the product of 1 minus 1 over p, where p is, this run through all the prime factors of n. And we can rewrite this a little bit as product of p to the alpha I minus 1, alpha I being the highest power you can divide n by of p, times p to the I minus 1. Note, so if n has any odd factor, then p to the I minus 1 is even. If n is greater than 2, and only has even factors, it must be some power of 2 greater than 1. So this must have at least 1, 2 out here, so it must be even again. So we conclude the totient function of a number greater than 2 is even. And so we can say the greatest common divisor of the totient function of m and totient function of n, assuming m and n are both greater than 2, must be greater than 1, since the greatest common divisor of two even numbers is at least 2. So now let's say we have an arbitrary integer divisible by two distinct odd primes. So let's say we have some arbitrary w equals p to the 1 to the a1 times m, where m is divisible by another odd prime and greater than 1. So we know from Euler's theorem, C, the Euler's totient of p to the 1 a1 is congruent to 1 mod p1 a1, assuming C and p1 a1 are relatively prime. Same for some arbitrary b relatively prime to m. B, the totient function of m, is congruent to 1. And from our previous results, we can say, so saying for some c, c of the totient m, c of the totient p1 a1, and these m and p1 to the a1 are both relatively prime. So using our previous results, we can say c to the totient of p1 a1 times totient of m divided by the greatest common divisor of these two totient functions. See, that power is congruent to 1 mod w, which is just m times p1 to the a1. And note that this top part here is just the totient function of w, because this function is they multiply together. Totient of A, totient of B, if A and B are relatively prime, goes totient of AB. And we know the denominator here is greater than 1 from our previous result. So we have C to the totient of W divided by some integer greater than 1 is going to 1 mod W. And so C cannot be a primitive root, regardless of what integer it is. And so we conclude that if we have something that's divisible by 2 unique odd primes, it cannot have a primitive root. And that solves our problem. Thanks for watching. Please check out centermath.org, check out our blog, and follow us on Facebook and Twitter. Thank you.